Hello, this is Team STARC, and in this video we will be sharing the motivations, goals, and scope of our design, as well as demonstrating the working product. Our design was created to autonomously control 4 gas flow rates and the furnace temperature in a looping cycle while recording data. This will enable the Solar Energy Research Facility team to test a chemical sponge by exposing it to hundreds of cycles of oxidation and reduction. The gas flows through the mass flow controller, which only lets the preset amount of each gas through. From there, the gas goes through the solenoid, which can have gas either flow to the room or to the system. The gas that continues through the system then goes to the gas flow combiner. It is here that the 4 separate lines, each capable of running independently and with different gases, combine. The gases mix together into one homogeneous mixture. This mixture would then move into the furnace. It is here that the combined gas would mix with the chemical sponge and release different gases as it heats up to 1800 Celsius and down to 900 Celsius in a continuous cycle that could run for as long as wanted. From there, the gas moves to the T-split. The gas then can move either to the pressure sensor, which reads the pressure in the system compared with the atmosphere, or through the filter. This filter slows down the gas and builds up the pressure in the system, allowing for the pressure difference to be significant enough to be properly read.
LabVIEW is used to interface with 2 NI DAC modules, the 9201 for outputs and the 9264 for inputs. Outputs include mass flow controller voltage, temperature, and pressure. Pressure is used to calculate flow rate, as seen on the top left of the LabVIEW front panel. Temperature is shown below, along with a graph for visualization. The box to the right of the graph is for editing file name and pathing for collected data. 5 stop buttons are shown on the left side. The one labeled anomalous condition controls all others, functioning as an emergency stop. The arrays allow for configuration of temperature set points, timings, and mass flow controller configuration. The first 2 values in each array are for startup, and the following 4 are cycled through n times. The 4 graphs on the bottom show set point and flow rate voltages for each of the mass flow controllers. As the system runs, the LEDs provide a visual indicator to which stage of the cycle is active.
The electrical board is responsible for providing power to the mass flow controllers, solenoids, and pressure sensor. In addition, it routes control signals and data from all these devices to the Data Acquisition Unit, or DAC, which interfaces with the computer. For better organization and ease of future changes, the lines are color-coded according to function. The red lines are hot lines for power, which ranges from 5 volts DC for the pressure sensor to 120 volts AC for the solenoids. The yellow and white lines are ground, which are all connected on the ground terminal blocks. The green lines are 0 to 5 VDC control signals originating from the DAC. The blue lines are incoming data from devices such as the MFCs and pressure sensor.
First, the pressure sensor is showing the pressure of the compressed air going through the mass flow controllers in SCCM. This pressure is used to find the flow rates through the MFCs. Next, we have the temperature reading on the graph in degrees Celsius, which matches the input that we have here on the temperature target. The given temperature is held for a certain time, as given in the box right adjacent to the temperature. The other 4 tables show the mass flow controllers cycling through the given number of cycles. Following that, the green lights show the MFCs and the relays are turned on and cycling through the temperature, while simultaneously the bottom 4 graphs show the corresponding voltage output. The white line is what we have input, and the red line is what we've been reading. The red line seems to be slightly offset, which is caused due to the delay that we programmed to get the MFCs to reach the required flow rate. As you click on this stop button, which is the master stop, we see that it starts off all the procedure as designated.
In conclusion, we first started with an overview of the motivation and goals of our system. Then, we discussed the scope and function of each major component of the design. Finally, we showed a demonstration of the product in operation.